So, majorly, if we talk about the sections that we're going to cover in this particular training, it's going to be network fundamentals. Then we're going to talk about something called network access. Then we will talk about IP connectivity. And then the fourth section will focus on things like IP services. And the fifth section will focus on security fundamentals. And the sixth section, of course, will focus on automation and programmability. So we're going to focus on that, which will basically cover about IP, okay, cover about subnetting, cover about things like OSI and TCP, IP models. Okay, we'll talk about things like how network devices works, like routers, switches, firewalls, and some other devices as well. Then we will of course see about network fundamental knowledge about what are the type of communication, what are the type of I would say cabling standards. So we'll see all these network fundamentals in the first section. Okay, then we are going to move ahead with network access, in which we will see how layer 2 operation works. Okay, over here in network access section, we're going to see how switches learns its MAC address tables, how VLANs and things like trunking works. We will see how ether channeling is done. So majorly we'll focus on layer 2, okay, of the OSI model in this. And then in IP connectivity, we will talk about how I would say layer 3 operation works. Things like routings and things like routing tables and routing protocols. Okay, we'll talk about that. And then in IP services, we'll talk about some of the features of how actually DSCP works, okay, how network address translation works, how ACL works, how WAN technologies works, how QoS works, and all these services that we use by using IP. Cool. And then in security, we will see about features like how AAA works, okay, authorization, authentication, and accounting. We'll see how like securing network. Okay, we'll talk about data security and some other. And in automation, we'll get an introduction to what is netconf, what is restconf, and how do you like automate networks using Cisco platforms by consuming Python. Okay, so we'll also kind of perform a lab in which you will see that how do you actually configure a device by using Python script and not by accessing the CLI that Cisco gives you. Now, as you already know that Cisco have came up with the new certification standards, because earlier Cisco used to have different tracks and different levels of certification as a certification track. Correct? So if we talk about the levels of the certification that it had, then you had CCNA, you had CCNP, and then you had CCIE. Correct. The CCNA stands for Cisco Certified Network Associate, which was the first level. Then the second level was Cisco Certified Network Professionals. And the third level, of course, is Cisco Certified Internet Expert. Cool. And these levels focused on different tracks as well. So you had routing and switching, you had wireless, you had data center, you had cyber ops, you had collab, you had service provider, you had cloud, correct? These were you, of course, security. These were different tracks in which you could pursue CCNA, CCNP, CCI. So for example, you could do CCNA in routing and switching as well. You could do CCNP in wireless, CCNA in data center, CCNA in CyberOps, CCNA in collab. You could do CCNA in almost each of this particular technology that is mentioned in tracks. Make sense? And then you could pursue CCNP later in routing and switching once you're done with CCNA as your second step towards moving towards your CCI. Cool. And then you could do CCNP in wireless. So you could go with choosing specialized courses. But what Cisco have done now, Cisco kind of first of all renamed this RNS to something called Enterprise, and all these tracks now starts at the CCNP level. So you do not have the ability to choose CCNA for either RNS or wireless or data center. There is just single CCNA. And what they have did when we talked about the concepts of these, they have kind of merged some of the concepts of routing and switching, okay, of wireless, of security, of data center. These are the four major streams or major tracks from which they have pulled out some of the important concepts and merged it into the content of the new CCNA. And they have recently introduced automation as one of the new concepts that focuses on section number 6 of this particular course or the particular module. So that's exactly how Cisco is running its new CCNA. That doesn't say either it's part of enterprise or wireless or security or data center. It's kind of merge of the most of the important technologies that you have. Okay, and then in earlier, I would say certification standards, if you had to do CCNP, then there were a set of exams that you needed to pass. Okay, for example, in CCNP routing and switching, there were three exams. One was a route, the second was switch, and the third one was T-shoot. Cool. This route, switch, and T-shoot, all of these three exams needed to be passed in order to become a Cisco certified network professional in routing and switching technologies. But in newer certifications, the thing is that you still have CCNP routing and switching, but it has been renamed with CCNP Enterprise. And in all the CCNP certifications, you have one core exam and then you have one concentrated exam. These are the two exams that you need to give. So the core exam basically is mandatory, and the concentrated exam focuses on different technologies that that particular track, I would say, focuses on. Just like if we talk about enterprise network, so enterprise network focuses on SD-WAN. Okay, enterprise network focuses on stuff like DNA or stuff like NRC, which is advanced routing and switching. Okay, stuff like troubleshooting. So you can choose any one of this particular exam. Okay, so this would be your one exam plus the core exam. So the core plus concentrated. These two exams would make you CCNP enterprise. And just like that, there is a core exam for each and every track that is available over here. You have a core exam for wireless, for data center, for collaboration, for service provider, for cloud. Now, there is no cloud anymore. Okay, the cloud has been renamed with data center itself. So people who had cloud certifications are awarded with equivalent data center certifications nowadays. So that's exactly how it works over here. And then what we are going to see now is CCNA that focuses on the new concepts. Okay, so that was just kind of a brief intro to how Cisco is moving further with their certifications. Okay, the exam number for CCNA is 20301. Okay, that's the exam number that we're going to follow. And you can Google about the details that are available over there. So let's move towards the content as we have. When we talk about introduction to network, what do we call a network? Most of the networking classes starts with the same thing, right? What do we call as a network? So whenever you have this, the most standard definition that you might have heard is whenever there are two or more computers that needs to be connected together, okay, you call it a network. For example, there is a guy over here that uses a PC, and let's name it as PC1. And then there is a guy that uses PC2. Correct? Whenever we connect these two devices together, how can we connect it? The connection can either be wired or the connection can be wireless. Okay, it can be a wired connection or it can be a wireless connection. Whenever these guys are connected together, then they can communicate in a network. We can call this entire thing as a network. And of course, these two PCs needs to be named. They need to have some name. Let's assume that there is a person, very skinny person, and that particular person is saying, "Hello, how are you?" Okay, and the message is going from, let's say, uh, AB to DB. Cool. These two are the persons over. So AB says to DB that, "Hello, how are you doing?" Cool. Now, if how would this particular communication take place if AB doesn't know the name of DB? Okay, if you go out and communicate with your friends, you of course address them by their names. Just like that, whenever there are devices who has the ability to connect over I would say a network, needs to have a specific name. And what are called as names into the world of networking, we use something called IP address. And you must have seen IP addresses like 192.168.1.1, or let's say 192.168.1.2. Correct? You must have seen IP addresses like this in your I would say in your life. Cool. So each and every computer, each and every mobile device, each and every I would say device that can be connected over the internet does have some sort of IP address assigned with it. Without that, it cannot communicate with the other computers over there. Make sense? And there are classes and different ranges of however this particular communication works. But whenever these communication kind of increases, meaning the capacity of the people who are being connected in the network increases. Let's say there are multiple people. Now, if we have PC1, PC2, and PC3, these three PCs needs to be connected together. Can they be connected in like this manner? They cannot be connected like this, right? Because what happens is whenever you see a cabinet of the PC, which we call it as CPU, your CPU just has something called NIC card. You can Google this, right? And this NIC card has an Ethernet, I would say, connection, and you can use this Ethernet cable in order to connect with this NIC card. Now, in 90% of the CPUs that you would see in your life, there will just be one NIC card installed onto the CPU. However, you can install multiple NIC cards on your PC. Make sense? But as most of us do have only one NIC card on our CPUs, we need a centralized device that can accommodate multiple people on a specific network. So how do we solve this particular problem? We take help of different devices, and devices like routers, devices like switches. Correct? So what do? You take couple of PCs that needs to be connected. Let's say these are the four people that we need to connect together, and you accommodate a switch. Okay, and then you connect these devices together. Now what is a switch? Okay, the switch like something. Let me show you how does a switch look. This is how most of the switches looks like. So switch is nothing but a product which has these multiple ports that are used in order to connect multiple devices together. So just like that, whenever you have a switch with you, you can connect multiple ports, okay, with these switches together, and you can accommodate multiple people on your network, and you can name them like 192.168.1.1 and 192.168.1.2 and 1.3 and 1.4, like that. You get it? So whenever these computers are configured with some IP addresses, then these people can talk with each other. Make sense to you? But these computers also has some other details as well. So one of the major important thing that these computers are configured with are called as IP address. And the second thing is MAC address. Most of you must have guessed it, right? So IP address, we call it as a logical address, correct? And MAC address, we call MAC address as physical address, because whenever we purchase an NIC card, let me show you the NIC card also. So whenever you see this, this is kind of an NIC card, and there is a port that you can connect, I would say, your Ethernet cable. So with each and every NIC, there comes one MAC address that is always associated with this NIC card. Make sense? So this NIC card is hard coded. That's why we call it as physical address. Okay, and it can never be changed. However, you can change logical addresses, means one IP for an instance can accommodate with an IP address of 192.168.1.1, and maybe the next day that gets converted to some other IP address. That's possible. But the MAC address will always stay same. It will never be changed. Cool. So these are type of the addresses that most of the time you have on your PC as configured ones. And for each and every communication that you do, you will always use these NIC cards. Make sense? So our part starts with that whenever you kind of build a application, there are different topologies that builds. We are talking about these, I would say, topologies that says there are four different connected, but you can have bigger networks as well. And there are different of networks that can be connected in your network. For example, if we talk about type of networks, then first of all, you have smaller networks like personal area network, and we call it as PAN. Correct? For example, whenever there is a mobile phone, and that particular mobile phone is, I would say, sharing some files, okay? And those files are being shared by using an application called Share It. You must have heard. Share It is kind of an application that almost everyone uses in order to share the files. Correct? So whenever you, what kind of resource do you use in order to be able to connect with the other device? We use most of the time Bluetooth, correct? Or you use I would say something called hotspot. By using technologies like this or NFC, near field communication, by using such technologies, you are connecting two different devices together or more than two different devices together. But the limit is very smaller. Okay, the I would say the physical distance that you can that makes you able to connect with these devices is smaller. Cool. So that's why we call it as a personal area network. When the network gets bigger and bigger, there are other additional networks like campus area network that connects devices in a specific campus. We call it as CAN. And then there comes different networks, major networks called LAN. Then you have MAN, and then you have WAN. LAN stands for local area network. MAN stands for metropolitan area network. And WAN stands for wide area network. Okay, so whenever you have a specific house, and in that house there are different PCs, and these PCs needs to be connected by using a switch. So this is how the connection looks like, and you call it as LAN 1. And when you connect different LANs together, LAN 2 or let's say LAN 3, and you connect it by using some sort of centralized device like a multi-layer switch or so, then we call it as metropolitan area network. And this metropolitan area network is combined with another metropolitan area network, Okay, by again using some centralized device. Then we call this bigger network as WAN. And internet, the best example of this wide area network is nothing but our internet. Internet is called as WAN itself. Do you understand that? That's exactly how these terms are like located. So when we talk about LAN, the LAN can only span till around 100 meters. Okay, how would you connect it? By using some cable or so. So you cannot connect two computers for more than a distance of 100 meters. If you do so, there will be some, I would say, noises, or your data might be corrupted when it gets delivered onto the destination. So that's why it's advised to not connect any devices that has physical distance more than 100 meters in a local area network. Okay. Otherwise, you can build up your metropolitan area network. So if we talk about, I would say, real time examples that where these networks are used, LANs are used mostly in offices. However, MANs are basically used, metropolitan area network basically are used in order to connect cities or states. Okay. And WAN is used in order to connect countries. Okay, so you can say that offices in a specific city can be connected by using local area network. And then cities or states can be connected together by using metropolitan network. And wide area network can connect multiple countries together. This is how the internet has been built. Okay, but apart from type of, I would say, networks, there are devices which are used in order to connect them, like routers and switches and firewalls. Okay, and there are different devices as well. However, you can talk about that there are multiple type of communication as well that you need to know. So when we talk about type of communication, the first type of communication is unicast. Okay, a unicast means one to one communication. Cool. There is a person that can talk with another person, and we will call it as unicast communication. Then the second part type of communication is called as multicast. And multicast communication means one to many. It can happen that there is like group of people sitting in your classroom, and this classroom has group A, group B, and group C. And the teacher is starting right over here, and teacher wants to talk with like group A. So that particular communication will be called as multicast because the teacher is talking with a specific like set of persons. Okay, but teacher is not talking with all of them. Okay, and when teacher is talking with all of them, we will call it as a broadcast. So that's kind of the real example that you can say, and we call it as one to all communication. Type of communication differs. You see that? So we will be learning about how this communication works as well. And yeah, then there are different, I would say, cabling standards as well that are followed. So when we talk about cablings, then you have UTP. Okay, or majorly if we talk about the types of cables, then you have a copper cable and you have a fiber cable. Cool, these are the two type of cables that you have. In copper as well, there is UTP, which is unshielded twisted pair cable, and then there is STP, which is shielded twisted pair cable. Okay, this UTP cable basically doesn't have any, I would say, shielding or so. And if we see the example of it, you can see that with UTP cable there is no aluminum foil that covers each and every pair of that particular. So you'll always find that in UTP cable there is always a color coding that follows. You can see the colors like blue, white, and blue, then orange, white, and orange, brown, white, and brown, and green, white, and green. These are the eight pins that you will find and each and every copper cable that you will see that gets used for the communication purposes. Make sense? And whenever these cables are, I would say, used, there are always two type of cable, UTP and STP. Internally, both of them work same, but STP cable is used for outside environments. When I would say like broadband provider is connecting multiple like broadband connections by using STP cable. And UTP cable is used for internal purposes, meaning whenever you're connecting different local area networks by using this UTP cable in your office environment or in your home environment or so, where there is no outside damages that can be caused to the physical cable. But STP is kind of a stronger cable, not easy to break, so that it survives all the atmospherical changes in our day-to-day life. Like it can survive summers as well, it can survive winters as well, and rains as well. That's why that STP cable is costly and it is used for outside environments. And UTP cable cannot survive all these different atmospheres. That's why it is used for inside environment or in-house environments. So that's why it's also cheaper and we everyone can afford it. Okay, and you must have seen that most of the time the installation charges that our broadband providers takes is due to the expensive cable uses that it gets involved, because they need to lay down the STP cable from one end to your home in order to provide you broadband connection also, and that's what they charge us for. Okay, so that's two type of cables that you can see, and there are different type of communication that also needs to be done. Either we are using UTP cable or we are using STP cable. It actually depends on the type of connection that you have, whether you are connecting a PC with another PC or whether you are connecting a PC with a centralized device or same or different devices. So, based on the cabling pins that you have, okay, you have 8 pins over there. You have pin number 1, 2, 3, 4, 5, 6, 7, and 8. And all these 8 pins are paired together. 3 and 4 will be paired together, 5 and 6 will be paired together, and 7 and 8 will be paired together. That's how these 4 pairs are used. Okay, and these 4 pairs will be connected to a connector called RJ45, and this RJ45 connector is exactly what looks like the connector that you might have seen. Let's see how an RJ45 connector looks like. That's what an RJ45 connector is. So all those cables or 4 pairs of cable is inserted into this particular RJ45 connector, and then you create kind of an Ethernet cable of your choice, whether that can be an STP cable or a UTP cable. And most of the time we use a crimping tool in order to crimp this particular cable. And I would also show that crimping tool to you. If you see, this is how the cables are paired together. Okay, and after pairing them together, you basically insert that into a crimping tool, which looks like this is kind of the crimping tool that you would see. You insert your RJ45 connector over here and you punch it and your cable would be ready. Makes sense? That's exactly how you do it, and that's exactly how you make the cable ready. However, the fiber cable basically is altogether a different cable that provides a speed of around 1 Gbps. Okay, so you can send and receive data with the speed of light, I would say. That's why it's just a short, I would say, optic wire that is involved into the fiber cable. And let's see how that particular fiber cable looks like. Yeah, you can see that. That's exactly how a fiber cable looks like. So you have a high density polyethylene insulation, which is very damn hard to break. And then you have a copper tubing, and inside that there are steel wires. And in those steel wires, you will also see a jelly casing, and that jelly casing will have an optical fibers. And this optical fiber, I would say, small pins will forward the data with the speed of light, so it doesn't cause any noises or so to that particular core. Okay, that's how the fiber cable looks like. However, the copper cable can have lot of noises in it. That's why it's not used just like that, and that's why fiber is so fast. Okay, so most of the time the ISPs are providing connections like fiber to the home now, where they directly lay down the fiber to your home, and you can actually have a high speed internet at your home. That's how they are working with it. Cool. So these are type of the cables that you have. However, there are different type of connections that you need to establish based on the devices that you're going to use. So there are a couple of technologies that is followed, and we call it as one type of cabling standard is straight through, and the other type of cabling standard is sorry, crossover cabling. So these are two type of cablings that you can do. Okay, and if we see it where this is used, then let's say that there is a golden rule that needs to be followed, that straight through cable is always used whenever you are connecting different devices together. Okay, and crossover cabling is used whenever you are using same devices. This is one of the rule that you can always remember, meaning that different devices is whenever you're using a PC and connecting that PC with a switch, let's say, okay, then the cable that you will use needs to be crimped according to the rules of straight through. Okay, but if you have a scenario like you are connecting a PC with another PC, then the connection must be done according to the crossover cabling. And what is the difference over here? You must have seen now that in copper cables, there are 8 pins that gets connected. Correct? So pin number 1, 2, 3, 4, 5, 6, 7, 8. And on the other hand, you will also find pin number 1, 2, 3, 4, 5, 6, 7, 8. Correct? This pin number 1, uh, 2, 3, and 6. Okay? I would say 1, we call it as TX. So let's say pin number 1 and pin number 2, whenever PCs are being connected, will be received as RX. And over here as well, RX and RX. And pin number 3 and 6 will be used as TX and TX. Make sense to all? So if we connect the cabling by using straight through mechanism, meaning that at point A of the cable, we are using first pin to be connected with the first pin. That is how the connection is happening. And connect pin number 2 with pin number 2, and pin number 3 with pin number 3, and pin number 6 with pin number 6. So what's happening is the data will be sent on pin number 3 and 6. And over here, the data will also be sent on pin number 3 and 6. So that's why the data will just go on a pin which is on an end which is not actually waiting to receive the data. That's the end which sends the data. And the receiving and receiving, both the ends will just keep waiting for the data to be received. So that's why we cannot use straight through cable whenever we are using same devices. We use crossover cable whenever we are connecting two like same devices over here. And what will happen in that case? In cases like that, whenever you have same devices and connected with a crossover cabling, you have RX and RX over here. You have RX and RX again over here. TX and TX, TX and TX. So you connect pin number 1 with pin number 3. You get it? Pin number 2 with pin number 6. And then you connect pin number 1 over here with pin number 3, and pin number 2 over here with pin number 6. That's how the connection is done. And as the connection is happening like crossover, that's why we call this type of cabling as crossover cabling. Make sense? And if we talk about different examples, let's say we replace this particular PC with a switch. So what happens over here? The pins that now used to send the data will be receiving the data. So over here we are also using pin number 1, pin number 2, sorry, pin number 1, pin number 2, pin number 3, and pin number 6. But pin number 1 is now TX, and pin number 2 also is TX. Pin number 3 is RX, and pin number 6 is also RX. So this receiving is straight away being connected with transmit and transmit. The TX with RX, TX with RX. That's how the different devices communicate together, and we use straight through cabling standard over here. Makes sense? Do you understand the differences between two of the cabling standards? However, this is kind of a thing that we used to follow in older, I would say, generation. But nowadays, there is a technology called Auto MDI-X. This Auto MDI-X is configured by default on all the devices. Okay, so newer network interface cards do support this kind of, I would say, feature. And it, with the help of this feature, the cable or the port automatically detects that with which device is it connected, and should it use straight through or should it use cross through cabling. So there is no need to crimp the cable according to the rules of straight through or crossover, because everything is over here. Make sense? So I hope that the basic fundamental thing about how cabling is done is understood by you guys. Okay. All right. So how about broadband internet? In which category it is? Broadband basically is just type of. So that actually depends whether the provider uses a fiber cable or a copper cable. The broadband is broadband. It's basically providing you internet feasibility to reach out to the outside internet. Whenever we are trying to develop a new topology that includes all the devices that we can facilitate in the topology, you will understand how broadband actually works. But as far as the cabling standard is concerned, then we can use either fiber or we can use either copper. Both of them will be called as broadband. Differences about multicast and broadcast is whenever, so multicast is basically used by media persons, okay, or I would say multicast is used by for internal communications as well by routing protocols like RIP, EIGRP, OSPF and all. So when devices needs to communicate with certain set of devices but not with all the available devices in a specific network, we call it as multicast. However, the broadcast can be kind of an example. Let's say you all watch TVs, right? Whenever you watch TVs or televisions, you see a specific program. That specific program is being streamed at 9 o'clock. Now, nobody can control that whether that particular program needs to be started at 9 or FM. FM is kind of another example. Radio is kind of one of the example that suits broadcast streaming. That at a specific time, the program just goes on air, okay, and that we call that particular thing as a broadcast in which everyone who is in that specific frequency or matches the frequency of the radio will start to listen to that particular broadcast that's happening. However, multicast is kind of a controlled transfer that the data will only get delivered to a set of people that are selected. But with broadcast, you cannot control that who gets the data. So that's kind of the difference between multicast and broadcast. Multicast is one to many communication, broadcast is one to all communication. Is there anything called Anycast? Yes, Anycast is a thing that was introduced with IPv6. So when we will be discussing about IPv6, I will cover Anycast. IPv6 doesn't support broadcast. It has unicast, multicast, and Anycast. And Anycast in comparison with the broadcast is one to nearest communication. However, we'll talk in detail about that whenever the IPv6 section comes up in this training later. So yeah. I hope you will go through working of Cisco Packet. Of course, I'll show you each and everything, and I will give you introduction to Cisco Packet Tracer as well. Okay, and we'll share the link from which you all can download Cisco Packet Tracer as well. So don't worry about that. Okay. Well, we are going to talk about centralized devices soon, routers, switches, and all. All right. So there is kind of a nice question that you can use whenever there are like devices like router to switch connectivity or router to server connectivity. The both the types of the devices are different. So for different devices, you will use straight through. You can follow the same rule. Even for router to server, you will use straight through. Okay. For switch to server, same straight through. For PC to server, straight through. Same thing. Different devices, same cable. RX basically is used for receiving, and TX is basically referred for transferring. Now we will talk about the type of ports, I would say, that we have, okay, or the type of Ethernet standards. So when we talk about these Ethernet standards, you have different Ethernet standards. The first one starts with Ethernet itself. Then you have fast Ethernet. Then third, you have gigabit Ethernet. And fourth, you have 10 gigabit Ethernet. Cool. The Ethernet kind of gives you the speed about 10 Mbps, which means that you can forward and receive traffic or data traffic with the speed of 10 Mbps. And with fast Ethernet, the speed with each standard kind of increases over here. With the fast Ethernet, you can forward and receive traffic with the speed of 100 Mbps. Okay, with gigabit Ethernet, you can send and receive data with 1 Gbps. Cool. And with 10 gigabit Ethernet, you can forward and receive traffic with the help of 10 Gbps. That's how speeds differ according to the Ethernet standards. Makes sense. However, the straight through and crossover thing still validates over here. So yeah, the only thing that you need to remember that whenever you are using uh, fast Ethernet or Ethernet, then four pins are used for data transfer and four pins are used for voltage. And whenever you move towards gigabit or 10 gigabit Ethernet, then all eight pins are used for data transfer and voltage. You see that? The thing doesn't differs like that. That only four will be used for data and four will be used for voltage. In gigabit Ethernet and in fast gigabit Ethernet, all the eight pins will be used. Make sense? So that's gonna help you over there. Cool. And then these are kind of the Ethernet standards that you use. Now moving forward towards the communication, that how does it actually happens? Then you can build up topologies, for example, like these are different PCs. Let's say that's A, B, C, and D. And when you have A, B, and C and D, then you can connect these devices with a centralized device in order to form up a local area network. We'll call it as a LAN. Cool. And this LAN can only be communicated whenever you keep it in a specific network. But in every communication that you do from here to here, correct, your PC needs to collect some of the data, and then the same data will be sent to the destination. And whenever the destination receives a specific data, then that particular data gets verified, and according to that, the contents are popped up into the onto the display that you are in. So let's say that you are sitting on a specific location. We are talking, or we are going to talk about reference models now. We talked about how communication and what do we call it as a network and type of communications. But the most important thing that we need to discuss on a very first day of this particular training is there are two type of models that you have. Model, and there is another model called TCP/IP model. Make sense? So this OSI model and TCP/IP model have have been the most famous models over there. But why do we actually need these models? Now, whenever the internet came up, okay, the internet was not that big. And what used to happen is companies back then tried to implement their protocol. So no matter what kind of service you use, if you are connected in a network like this, let's say that's your home router, and then that's your home switch, and there are a couple of PCs that are communicated or that are connected with this particular network. And then you have your ISP like AT&T providing you the connection, and then that particular connection is connected with the internet. Cool. So you want to reach out to google.com that is situated somewhere into the cloud, and then you send a request, and that goes on to the google.com, and then you receive it back. Correct? This is how the communication works. But upon each and every communication, upon each and every click that you do on your web browser, there is something called encapsulation and decapsulation. So you need to understand this thing pretty much. Okay, this is one of the most important things in your networking career that you need to be very clear with. Cool. So pay your attention over here while we are talking about encapsulation and decapsulation. But before that, you need to understand why even these models do exist. So it's just like the same thing that whenever the communication used to happen, there are different type of protocols that have been built. If you want to email someone, then there would be a protocol that is developed as SMTP, Simple Mail Transfer Protocol. If you want to browse a web, you will use something called HTTP. Okay, if you want to send some files, you will use FTP. If you want to, let's say, like fetch out some information of IP addresses or so, you will use ARP. If you want to download anything, you will use POP. So for each and every activity that you want to do on the internet, there is a dedicated protocol that has been developed. But back then, when internet came up, there were very limited vendors that used to manufacture PCs and that used to manufacture devices that could actually be connected onto the network. Okay, and vendors do existed majorly. You had IBM. Okay, and let's say there was Dell as well. Okay, and HP as well. These were kind of the vendors, and Apple as well. Okay, these were kind of the vendors that were there. What used to happen is whenever you connect a specific network, let's say you have a router or you have a switch, and that switch needs to be connected with PCA, PCB, PCC, and D. Now, if this entire network is consuming devices that are made up of IBM, then you would say that it will work. But if you are connecting something with a switch that has different set of devices, let's say you have a device of Apple, you have a device of Dell, you have devices of HP, and you have device of IBM, this thing will not work. I'm talking about the days of 1970s and 1980s when ARPANET and things like internet started to get famous. Okay, and the internet was rapidly growing. So back then, the communication like this was not possible. Why so? Because each and every vendor kind of developed their own set of protocols. So IBM had its own SMTP, okay, and then Dell had its own SMTP or HTTP or even ARP or anything. And each and every vendor had their own type of protocols. So whenever, let's say, the communication needs to be done from Apple to IBM, and it's kind of a communication which is FTP. So you're sending a file from Apple PC to an IBM PC. You will be using, of course, protocol like FTP, but that FTP of Apple didn't match with the FTP of IBM. And the easiest example that people do use is if there is a person that talks Spanish, and there is another person, girl probably, that talks French, correct? And I would say the Spanish person kind of talks with the French girl, and he wants to like appreciate the beauty of this French girl. So even though he tries to say anything, the girl wouldn't understand anything because the language that the French girl would understand is not Spanish. So the communication, they both are using languages in order to be able to communicate with each other, but the languages that they are using are not standardized language. Okay, and how they could improvise the communication, or how they could make the communication successful between them, right? There would be a breakup within 5 minutes, I would say. So if they would have used English, okay, or rather the Spanish guy would have used English in order to propose or appreciate the beauty of that French girl, then they would have landed up on top of the Eiffel Tower, I would say, and having a dinner. But without them being able to communicate with each other, yeah, without them being able to communicate with each other, they will just stay downstairs at the Eiffel Tower and go to their homes or hotels. And that's why this was kind of the same issue that you would find over here as well. That devices manufactured from the Spanish developer would not be able to communicate with the devices that are manufactured by a French developer. And that's why the organization, which is IETF, kind of proposed that there should be a standardized protocol or standardized model with each one should kind of followed. Okay. So if I give you a scenario that how things kind of started to grow back then, you can say that usually there were devices that had TCP model with it. Okay. And there was a model that was created by IBM, which we called it as DECnet. Cool. So the DECnet model then used to communicate with TCP, and then there came the others as well. So in 1980s, if we just talk about 1980s or 70s, there was just DECnet. And then in 1980s or 90s, then you had computers that followed DECnet as well. You had computers that followed TCP as well. Okay, but if we talk about 2000s, then you had computers that followed DECnet, you had computers that followed OSI, you had computer that follows TCP, and you had computers that followed others as well. And this is what kind of started getting popular. So that's why the need of something that is being standardized was there. Okay, so that the protocols, no matter what the protocols were, SMTP, FTP, okay, TCP, or whatever, these particular protocols needs to be standardized. Okay, DECnet doesn't stands for anything, but DECnet is basically a model that IBM developed. Okay, so and OSI was developed by some of the organization we'll talk about. The organization stands for ISO, International Organization for Standardization. Okay, and the TCP kind of got developed by Department of Defense, which is kind of a private development, but then that was the most logical model that was being used in most of the networks. So you can say that the two models that were famous and that were made standards were OSI at first, which was developed by ISO, International Organization for Standardization, and there was TCP/IP model that was developed by Department of Defense, US Army. Okay, and this OSI model is till now called as the most famous reference model that you can have. And then TCP/IP is called as the most logical model that that we use. So this is in use, okay, on devices, and this is in, I would say, this is what best for understanding. So we will understand how communication works. Okay, and what we are going to talk about with these particular things is encapsulation and decapsulation. Make sense? So as you know that we follow something called layered approach. Okay, we'll talk about how this layered approach goes, but each of this particular model has several layers in it, correct? And the layers go like application, presentation, then you have session layer, then you have transport layer, then you have network layer, then you have data link layer, and then you have physical layer. Cool. So we call this as layer number 1, 2, 3, 4, 5, 6, 7. These are the 7 layers that you have, and you can, I would say, remember these by saying, please do not throw sausage and pizza away. Okay. In most of the books that you would see the same thing over here, that you can use, please do not throw sausage and pizza away. Or in Hindi, that's our language, we say, please do not throw Shahi Paneer away. Cool, that's how we remember it. Yeah. So there are multiple ways that you can remember these 7 layers, but each and every time you kind of click on any information that you browse on the internet, be it Kylie Jenner pictures or be it Bradley Cooper pictures for girls, yeah, you do follow. OSI model kind of helps you to get those pictures on the boards. So we call encapsulation to something when the communication goes from PC to the destination. The information gets collected with the respective of top down approach, which means the information starts getting collected from application down to presentation, transport, network, data link, and session, like this. And then the information travels, and then the decapsulation happens like this. And encapsulation is top down approach and decapsulation is down up approach. Makes sense? So how does this particular communication works? Let's talk about what kind of information is collected at each and every layers. Let's check out. Yeah, so let's see how this particular communication works, and what kind of data is collected at each and every layer that you have over here. So whenever we are still discussing that how communication is going to happen. Let's say that you are connected to a router and a switch and a couple of PCs over here, right? And this particular PC is going to send some information on ISP end, and then there is google.com, and you are trying to kind of grab some information on from Google. So you are sending a request, okay, and then for this particular request to leave your computer needs to collect some information, and it will collect information for each and every layer that is mentioned over here. So for application layer, it will kind of try to see that what are the resources that are available on your computer that can be used in order to view the data. So we call the top 3 layers as software layers. Okay, then we call the transport layer as heart of OSI. And we call the network, data link, and physical layer as, I would say, hardware layers. You get that? So at software layers, it collects information about all the softwares or whatever the application that you're going to use. Okay, so at application layer, it kind of sees that at application layer, it's going to check that what all resources do you have in order to be able to view the data on your computer. For example, web browser. Okay, let's assume that you go in your college days or in days like that, like where you need to go to a lunch or dinner, and then at that particular facility where lunch or dinner is being served, there is a servant who is kind of serving the food onto the plates. So you just go in front of that particular person or the servant, and you just say, "Give me food." He's not gonna open up your mouth and pour a couple of like I would say, food or food directly into your mouth. Like open that up, it pours out some sort of like chapati as Indian food and some sabzi or there's some dish that has been made, and he just opens up your mouth and fills you up. That's not gonna how it go, right? He will ask you to get a plate, and then on that particular plate he's going to serve you the food. So we can assume the plate as kind of an I would say interface, and we can say that the food is our data. So you can say that the food is being served onto the plate, meaning that if we consider that the information that Google is going to provide us, let's consider that as our food. And where can we access that particular food? In something called web browser. So if you do not have a web browser, you will not be able to, or an application at least, you will not be able to see the information that Google can provide you. So that's the detail that it checks at the application layer. That does your PC has any information, or does your PC has any interface on which the data can be served? Okay, that's exactly the information that gets collected at the application layer. So you can say that applications or web browsers can one of the information that can be created, and it says whether it supports HTTP or whether it supports DNS or whether it supports DHCP. These are kind of the application layer protocols. Okay, that sits over there. As we talked about layered approach, the layered approach means that each and every protocol that is available out there in the world do sits or do follow some of the layers that it has. Like HTTP is an application layer protocol, IP is a network layer protocol, TCP is a transport layer protocol. Just like that, each layer that each protocol that exists today does sit or does fits into one of its layers. Make sense? So at application layer, it will collect the information that it needs, and then it will come down to presentation layer. Now at presentation layer, it's gonna do the work of compression and decompression. What does this compression and decompression means? Whenever the data is going to go from here to there, you are going to get a reply. And this particular reply will contain some of the data. That data might be into the form of text. The data might be into the form of MPEG-4 for a video. That data might be a JPG image. That data might be MP4 video. That data might be MP3. That it can be an audio. So each and every that you see, each and every data that you see does have some data format. And in what data format the data should be displayed or sent or received, that task is called as compression and decompression, and that gets done at the presentation layer. Make sense? So that's what the information is that physical sorry presentation layer kind of covers. Cool. And then it goes down to session layer. So at session layer, let me give you an example over here. You might have seen a web browser. Of course, you have seen. Most of the guys do spend their lockdown time in watching something. That's weird. So yeah, let's say that you use a web browser, and so when you're accessing a web browser, let's say that there are four different tabs that you have opened. Okay, the first tab is facebook.com, the second tab is yahoo.com, the third tab is google.com, and then there is a fourth tab, let's say youtube.com. Okay, and most of you might have an incognito window as well. But let's not talk about that. Let's talk about the non-incognito windows. So these are the four different tabs that you have: Facebook, Yahoo, Google, and YouTube. And let's say that the PC that this particular browser is using has an IP address of 192.168.1.5. Cool. Now, as this particular PC, which is having 1.5 address, is using different tabs in order to reach out to different servers. So can we say that Facebook is connected at 8.8.8.10, let's say, just for example? I know it's a global DNS address, and Yahoo is connected as 10.10.10.10, and Google is available at 12.12.12.12, and YouTube is available at 14.14.14.14. These are different addresses of the servers that they can be reachable. So can we say for first tab, the source is going to be 1.5 and destination is going to be 8.10. Cool. Then for second communication, the source is going to be 1.5 and destination is going to be 10.10. And for third, the source is going to be 1.5. The destination is going to be 12.12. And for fourth tab, the source is going to be 1.5, but the destination again changes to 14.14. Do you agree all this information? Now, this is when the data is going from our end to different servers. But whenever these different servers are going to send you the data back, what can we say that the source will now be different for each and every request or each and every reply, but the destination will just be same. Okay, the destination is just going to be 192.168.1.5. Okay, and the source is going to be different whenever all these servers kind of replies you back. So, does it ever occur in your web browser that these tabs kind of opened their information into some different tab? Like Facebook's data opened into Google's tab and YouTube's data opened into Yahoo tab. It never happens, right? Because the session layer kind of keeps different application data separate from each other by using port numbers, and it assigns different port numbers to each and every tab and each and every application that is open, and it keeps different application data separate from each other. Makes sense? It doesn't let that particular thing get involved with the other tab. Also, you might have seen payment gateway pages where the page itself says that the page will automatically be terminated in 180 seconds whenever you go forward and enter your Visa password or so. That kind of pages also are controlled by a session layer. So this is what session layer is responsible to. Okay, whenever we talk about its responsibility, the session layer keeps and maintains different application data separate from each other. Okay, do you understand this? I hope the example helps you. Yeah, all right. So I'll just write it in a clean manner because when we talk about OSI now, we said we have application layer, then we had presentation layer, then we had session layer, then we had transport layer, and then we have network layer, and you have data link layer and physical layer. These are the 7 layers that you have. Correct? And we talked about the first 3 layers are called as software layers. The transport layer is going to be heart of OSI, and the next layers are going to be hardware. Makes sense? The application collects information about the resources if that's available. Then the presentation collects the information. The presentation collects information about how the data should be displayed, and the session layer just gives different application data separate from each other. Now there is another thing called PDU, and this PDU stands for protocol data unit. This is kind of an extension and a field where this collected information is stored, and the field that it uses to store the software information is called as data. So the format of that particular information that is collected at top or the 3 layers, that is application, presentation, and session, is just data over there. Cool. Whenever it comes down to transport layer, the data gets added up and gets converted into a field called segment. And what this segment contains, or what this transport layer does, transport layer is one of the most important layers that you have in OSI model. Okay. And this particular transport layer just does the identification of whether TCP needs to be used or whether UDP needs to be used. Okay. And these are two of the most important protocols that exists into the history of internet. And how does this differs with each other? So TCP is called as a reliable protocol, and UDP is not reliable protocol. We'll just discuss about why TCP is reliable and why UDP is not reliable. Then TCP is called as connection oriented, and UDP is non connection oriented, or I would just say connection less. Okay, TCP kind of uses three-way handshake method. That's why it's reliable and that's why it's connection oriented. And UDP does not use that. TCP is slower and UDP is faster. Why so? Because TCP gives you delivery guarantee and UDP does not give you any guarantee that your data will be delivered. Okay, so to use TCP or to use UDP for the current communication, it decides what needs to be used, TCP or UDP, and it decides. TCP is basically reliable because it uses three-way handshake, and what it does is whenever, let's say, there is a PC and there is another PC, what it will do before sending the data, A will ensure that B is available to receive that data by sending a synchronized message. It will send, hey there, are you there? Are you available? Okay, if B receives that synchronization, it will send an acknowledgement of that particular synchronization that, hey, I'm available. Plus, it will send its own synchronization message as well that, hey, I'm available. What about you? Okay, shall we make a connection? Shall we make a friendship? Yeah. And whenever A receives its own it's like B's synchronization, then it sends its own final acknowledgement. And then they say that connected. Make sense? This is how connection is established by using TCP. And that's why A knows that B is there to receive the data. And after each delivery of data, okay, B is supposed to send an acknowledgement of the receipt that I received all the data that you sent. And that's how it guarantees delivery. And since it takes some time, that's why TCP is slower. However, there is no three-way handshake that gets done in UDP. That's why UDP is faster in order to send data. Okay, it's just like if we talk about real-time example, you must have seen, most of you guys might use WhatsApp for daily communications, correct? And when you use WhatsApp, when you open up I would say a contact of yours, or your girlfriend or boyfriend chat, then you see whether that particular person is online or not. Or you, most of the time, you would also see last seen messages if that's enabled or so, correct? And whenever you open the contact, the synchronization message gets sent. And if the destination device is online, it replies back that the WhatsApp application is on. And then the connection gets established and the online status just comes up right below the name of the contact. Okay, because it uses TCP for doing the communication. And it's one of the core reasons why breakups are happening nowadays. So yeah, that you are online, why don't you reply? All right. So that's what gets happened. It's TCP is basically cause of all those mishappenings in today's world. So, and UDP doesn't follow any of that particular shit. So whenever you do that, uh, you can say that TCP is used in mostly data sensitive communication. Okay, and UDP is basically used in real time communication. Whenever the data delivery needs to be ensured, you will use TCP. And whenever it's I would say the speed that matters, then you will use I would say UDP. For example, our live like cricket match, okay, or live streaming of any I would say broadcasting that's happening. You cannot use UDP over there. Let's say you most of you guys might have experienced network congestion in the early days of YouTube, right? We used to browse YouTube, and most of the time we used to see lags there. That some of the pixels of the video are being messed out. Okay, what would happen because YouTube uses UDP over there, because video is not kind of a daily sensitive data. Okay, or video is kind of you can say that the data delivery doesn't need to be guaranteed. It actually depends on the bandwidth that is available for the communication. So when you're using that particular communication, let's say that while browsing a YouTube video, some of the pixels were missed out. Now, if TCP is being used over there, those pixels would again send that particular, like the server will again send that data, because the acknowledgement was not sent from the client to the server for the sent data. Make sense? So if there are like message that needs to be sent, or there is a video that needs to be sent, and if destination doesn't receive that data, then it asks for the retransmission of that specific data. And in the case of YouTube video, while the video is still playing, the like I would say weird pixel would reappear over there, and it will kind of not be a good idea to use TCP over there. That's why there are still data. Like in the cases of voice and video traffic, we use UDP. In the case of I would say data, whenever that's plain data that is being sent, we use TCP because that needs guarantee over there. So yeah, all these things matters, and whether to use TCP or whether to use UDP is basically what is decided at transport layer. Now there are other things as well, okay, and we can call those other features of TCP as segmentation. Okay, then there is something called reassembly. The segmentation and reassembly means that let's say that you have a specific data that needs to be sent from A to B, and the data is a message called hello, how are you? Cool. And let's say that your bandwidth can only take one word at a time. So what you will do, you will kind of divide this data into different chunks. And all these data needs to be, or all these different chunks needs to be numbered. Okay, the numbers can be, let's say, 1, 2, 3, 4, 5, and all these different data would be sent out onto this link, and he will receive that, the B will receive that particular data, and it will also see the details that I need to receive 1, 2, 3, 4, 5. Okay, so and whenever these numbers are sent, then it will also be notified that how this particular chunk should be reassembled. So that's how the data is also sent by using the segmentation and reassembly. There are other features as well that you can explore on Google by learning deeper things about TCP and UDP. But yeah, the basic idea for OSI is whether to use TCP or UDP is gets that's what gets decided at transport layer. I hope that makes sense to you all. And then whenever it's decided that what needs to be used, it becomes segment. So segment contains details of either TCP or UDP needs to be used, plus it contains the data. Make sense? At transport layer, it gets decided whether TCP needs to be used or UDP needs to be used, and it becomes segment. Then it comes down, and at network layer, it will become packet. Okay, and packet will basically mean that what should be the source IP address plus what should be the destination IP address. Make sense? This particular detail will be chosen. Plus, it will contain the above detail as well, whether TCP needs to be used or UDP needs to be used. Plus, it will contain the information of data. And this entire content will be the thing that packet will contain. And then this packet will come down to collect information at data link layer, and it will get converted into frame. And frame will contain information about source MAC address plus destination MAC address plus TCP or UDP plus data. And combining this together, you get something called frame. Also, these are all the headers that are being associated, right? You get a network layer header that we call it as IP header. You get a MAC header that is being, or Ethernet header that is being attached as a frame. Okay, you get a TCP header that is being attached as a frame. So when we talk about header and trailers, these headers are basically added with the information. So when we say that there was just data, okay, and then we say that there is another information that gets attached with it, we call this as TCP information. So this TCP thing will be called as header. If there is something that gets attached at the front, we call it as header. If there is something that gets attached at the last, at the tail, that will called as a trailer. Like if we see the information of a packet, so a packet contains information about source IP plus destination IP plus TCP or UDP plus data, correct? This is your segment. With this segment, there is going to be source MAC plus destination MAC. This information is being added at data link layer. So we call this as Ethernet header. You get it? That's how headers and trailers are working. And then if we talk about the trailer, then so there is another thing that works at data link layer. Okay, the data link layer also does the job of error detection. There is additional feature of error detection that happens at data link layer. And how does it do that? It performs a mathematical calculation which we call as CRC, that stands for cyclic redundancy check. This CRC basically ensures that the data is not corrupted. Okay, and this is kind of a mathematical calculation that gets attached, the value of it get attached at the end of this particular frame, and we call it the field is called as FCS, frame check sequence. Okay, and it is nothing but an Ethernet trailer. So the Ethernet trailer contains a field called frame check sequence that performs a mathematical calculation which is called as cyclic redundancy check in order to ensure if the file is corrupted or not. Okay, the source IP and destination IP is mentioned over here. This is kind of a packet. I didn't miss that. So in packet, you have source IP, destination IP, TCP IP or TCP or UDP plus data. And then with Ethernet header, it attached source MAC and destination MAC. And at Ethernet trailer, it attached frame check sequence. So that's exactly how it works over here. Cool. And then after collecting all this information, this particular thing will become a frame. Okay, and the frame will forward the information down to the physical layer. So it will come down, and this physical layer will kind of convert the information into bits. Okay, and all this information will be converted into bits and then forwarded to the destination. Yeah, checksum is kind of the same as CRC, I would say. Cool. So this information that is being collected over here will be called as a process of encapsulation. Cool. And then the bits and bytes will be forwarded there. And then the destination device receives the information and it just opens up each and every layer one by one and reaches out to the, I would say, reaches out to the application layer by following the bottom up approach, and we call that approach as decapsulation. No, at frame, the basically the entire frame contains the IP address, but it doesn't confirm, like it doesn't go with the information of, so I would say, source IP and destination IP. It's all about information that gets added at each and every PD. So at segment, it will add information of TCP and IP. Segment just contains information about TCP UDP. Okay. The network layer basically just forms up a packet by considering and adding information about source IP, destination IP. The data link just like converts it into frame by adding information about source MAC, destination MAC. Yeah, I forgot over here. Plus, it will also have source IP and destination IP. Okay, plus TCP UDP plus data. That's what the information will be over there. And all this information will be converted into bits and bytes and will be forwarded to the destination device. Okay, and then the destination device will receive the bits and it will convert that analog data into again digital data and will unfold each and every, I would say, layer and will be receiving that information. This is just one part of the communication. This is how the request gets sent from one location to the other location. The communication is not initiated by any specific layer. The communication is initiated by the PC itself. That you want to do certain, I would say, certain transaction. FCS is added over here uh, at the data link layer. Preamble is kind of an extra field at the data link layer that gets added over here. For that, you will specifically need to go into CCNP level. This is all information that gets talked or that gets discussed when we talk about CCNP. It will not be relatable over here to talk about all each and every field that is there into each and every packet. Okay, or that is there into each and every header. We're not discussing about OSI headers. We're talking about general concept of OSI. And when we move further, we'll see how these things unfolds. Cool. So this is exactly how encapsulation and decapsulation is followed. Okay. And when we talk about, I would say, let's keep it like here. When we talk about communication that is happening from one end, when you have devices like this, and then that those devices are connected to ISP routers, and this ISP is connected to internet, and this internet is again connected to different devices or let's say servers. And when you send traffic from here, that goes from here to here to here. This is exactly what the process gets followed for just sending out the request. When you will receive a specific reply, the same process will happen from server end to your end as well. Like server will kind of encapsulate the traffic and then send the traffic and receive that particular reply at the destination, and destination will kind of do the work of decapsulation. Makes sense. Then whenever you have a Google, I would say, responses in your screen, you again click on certain link, again encapsulation happens and then sends the data, and decapsulation happens at the server end. So this encapsulation decapsulation just works at each and every layer that is available over there. You get it? So between each and every transaction that you do in OSI model, okay, all the seven layers gets treated. However, OSI is not kind of a logical model that we use in like that our PC understands. What our PC understands is basically TCP IP, right? So if we compare the thing that are available as compared to the OSI contains application, presentation, then you have session, then you have transport, then you have network, then you have data link, and you have physical. However, if we just talk about TCP IP model, then you have application, okay, then you have internet layer, Cool. Or we'll just write it down as equivalent over here. You have internet layer, you have a network layer, okay, and you have a physical layer. So what happens is all these three layers, application, presentation, and session, are shrinked down to application layer of TCP/IP. Cool. So all the work of application, presentation, and session is just done by I would say, it's just done by the single layer of TCP/IP, that is application layer. Then transport layer is converted into internet layer. The work is just same over there. And then network layer is converted into network of TCP/IP. That's again same. And the data link and physical layer is converted into just single layer, that is physical layer. So TCP/IP just has these four layers, but does the work of all seven layers over here. Make sense? That's how the comparison is, and the work is almost like same. Okay. So you have kind of, I would say, data over here, you have segment over here, you have packet over here, you have frame over here. That's exactly how the thing goes. Okay. And since I would say late 1990s or 2000s, the term TCP/IP has become the most standard and most logical, I would say, model that each and every PC that is out there, or each and every device that is out there that can be connected with the internet, follows. So that's what our TCP/IP, and that's what OSI model can work over here. Okay, and I hope you understood the basic, I would say, meaning of how this logical or how this reference model works. Okay, by looking into how encapsulation and decapsulation processes are executed. So that was our today's agenda in order to discuss the very fundamental knowledge about networking, how networkings can be done, what is a network, how devices can be connected together, okay, and what are type of communication, the type of cables, the type of connections that you can do. Okay, then we discussed about the Ethernet standards that are available. Then we moved into understanding how this OSI model and TCP/IP model works. Okay, that was our major motive and agenda of the first day of this particular training. Our tomorrow's agenda will be in order to discuss IP addressing. We will talk about different classes of IP addressing, the types of IP addressing. We'll discuss IPv4 there. Okay, and then we'll see how subnetting works, and then we will try to get an introduction to Cisco Packet Tracer. So we'll be sharing a link with you where you can download this particular thing, Cisco Packet Tracer, and you'll get to know about it. Okay, we'll discuss, and we'll probably do a small lab on connecting and building a local area network by using different devices. All right. Thank you. Thank you everyone for tuning in. I'll see you guys tomorrow at the same time.